Welcome back. We are in chapter 4 of Fundamentals of Electronics. In this chapter, we will discuss some special purpose diodes. So when we discuss the special purpose diodes, let us see the introduction first. We have seen the rectifier diodes in the previous lecture, which will convert the AC voltage to DC in the power supplies. And this has been taken very detailed in lecture number 2 and 3. So the purpose of the diodes beyond rectification, which serves in various applications, we will see. So diode may serve beyond the work of rectification. Rectification means conversion of AC voltage to DC voltage. In the special purpose diode, the first category that we will take is basically the Zener diodes. These Zener diodes are optimized to work in the breakdown properties, and it is essential for voltage regulation in the circuits. So we require voltage regulation in the circuit, and basically it work in the breakdown region. So Zener diodes are the special categorized special purpose diodes. Apart from the Zener diodes, we will discuss other diodes such as the optoelectronic diodes, example the LEDs, which are the light emitting diodes, the Schottky diodes, also known as the low forward voltage drop diodes, the varactor diodes used for variable capacitance, and many other additional special purpose diodes also we will see in the lecture 4th. So what are Zener diodes? If we talk about the operation, unlike the small signal and the rectifier diodes that we have covered, the Zener diodes are designed to operate in the breakdown region. So the region of interest for the Zener diodes is in the breakdown region, and they are the backbone of voltage regulators, which will maintain a nearly constant load voltage despite the fluctuations. So whatever the fluctuation we see at the input, the load voltage will remain the same. There is no change in the load voltage, and this is being accomplished with the help of the Zener diodes. If we talk about the schematic symbol of the Zener diodes, so here you can see two different ways by which the Zener diodes are represented, with a symbol Z, which is indicator of that the diode is in the form of Zener diodes. So the head of the diode is in the form of the letter Z, and hence it is known as Zener diodes. The breakdown voltage usually vary from 2 volt to over 1000 volt depending upon what doping level has been used for the diode, for P-type or N-type semiconductor. When we talk about the current voltage characteristic of the Zener diode, there are 3 important operating regions. The first region is known as the forward region, second region is the leakage region, and the third one is the breakdown region. Forward region, it is like the normal regular silicon diode which conduct at 0.7 volt. So you can see the first quadrant of the current voltage characteristic, which is similar for all diodes which conduct after 0.7 volt, which is the forward conduction voltage. And there is a small reverse current which is there between 0 and the breakdown. So if we talk about the curve which is there between the 0 value and the breakdown value, this region is known as the leakage region. The breakdown region is shown by a sharp knee followed by a near vertical increase in the current. So there is a increase in the current in the reverse biased, and the voltage stays approximately constant. So here you can see the voltage remains the constant, which is Vz in the breakdown region. So in order to operate safely the Zener diode, the maximum reverse current, so we have the current which is maximum in the reverse biased given by IZM. So if you exceed this current IZM, it will lead to diode destruction. So any current below IZM is fine, but if you increase the current above IZM, then the diode will burn out. So there is a current limiting resistor which will be essential to protect the diode. So generally we will use one resistor which we will put between the source and the Zener diode, so that the maximum current is being limited to protect the diodes. When we talk about the Zener resistance, usually we go with the third approximation of a diode. If you remember, we have discussed the second approximation in the previous lecture when we discussed the diode circuits. So the forward voltage is nothing but the summation of the knee voltage plus the voltage across the bulk resistance, which is due to the semiconductor properties offering the resistance. We have discussed what are bulk resistance in the previous lectures. The reverse voltage is the breakdown voltage plus the voltage across the bulk resistance. Now here, since the resistance is in the breakdown region or in the reverse region, so we are talking about the Zener resistance. Zener resistance is defined as the inverse slope of the current voltage characteristic. We know from Ohm's law that if we draw the curve between current voltage, we get a straight line, and the slope of this curve generally represent the resistance, which is for any normal VI curve. So VI curve, when we see in the breakdown region, then the inverse slope is basically defined as the Zener resistance in accordance with the Ohm's law. So we have V equal to I into R. So we get R is equal to V by I. Here the curve is drawn between the current and the voltage. So the inverse slope we take for the IV characteristic. So when we get more vertical breakdown region, then it will be indicator that smaller Zener resistance is there. So what effect do it has on the reverse current? So increase in the reverse current leads to slight increase in the reverse voltage. So we have seen that voltage has to be constant, but if you increase the current in the reverse region, then there will be a slight increase in the reverse voltage. Typically this voltage increase in only a few tenth of a volt. So it is slight because the voltage has to be constant, which is equal to Vz. When we talk about the design considerations, Zener resistance matters in design, but is often ignored in troubleshooting or preliminary analysis. So in that case, we take only ideal diodes. So we do not take the Zener resistance into account. It is only in the troubleshooting or when we are doing some preliminary analysis for the diodes. If we go by the visual representation, the typical Zener diodes are being shown like this, which are having different numbers given to it, and we use these type of diodes in the laboratory for various experimental purpose. The Zener regulator, as we have seen that the Zener diodes will be used as Zener voltage regulator so that a constant output voltage is maintained even when the current changes. So although the current is changing, but the voltage will be constant. So it requires a reverse bias for normal operation. Generally, the Zener diode will operate in the reverse bias region. So here you have the source voltage denoted by Vs. The voltage of the Zener diode is given by Vz, and there is a current limiting resistor Rs. If we note here that the Zener diode is reverse biased with respect to the source, so reverse current will flow. Operating conditions, you have the source voltage which is greater than the Zener breakdown voltage. So Vs will be greater than Vz, then only the current will be flowing, which is the Zener current. And a resistor is used to limit this current and prevent any burnout. So we have seen that in the reverse region, when there is sharp increase in the current, then the current should not exceed the maximum current, and this is being limited with the help of the Zener resistance. If you want to measure the voltage with a source, Zener resistance and the Zener diode, then we basically take and measure the voltage across the Rs with respect to the ground. So we get the voltage Vs and Vz, and if we subtract this voltage, we will find out what is the voltage across the Zener resistance. In order to use the Zener diode as voltage regulator, now this is a practical circuit where the output Vs or the source voltage is coming from the bridge rectifier that we have discussed very detailed in the previous lecture, and you are also using some capacitor input filter, which also we have covered, and you get a voltage Vs, which is the output of the source. Then the current will start flowing because it is a closed circuit, and the Zener regulator provides a DC output voltage which is less than the power supply output. Note here, this Vs is also a DC voltage because it comes from the rectifier, and the Zener voltage Vz is there in the Zener diode. The current will flow in this circuit, and the source voltage will be more than the Zener voltage. So commonly, this Zener voltage regulator is used for voltage regulation in the circuit. So even there is a fluctuation in the source voltage, the output load voltage will be constant, which we will see in the coming topics. The Zener regulator for the current calculation, if we want to calculate, then the current which is flowing in the circuit, which is in the form of a series circuit, then the current is given by the difference of the source voltage and the Zener voltage divided by the Zener resistance. So this is again from the Ohm's law. So the current Is, which is the Zener current, because it is equal to the source current also, because it is a series circuit is there and the same current will be flowing in the Zener resistance and the load. So the current Is must be lesser than the reverse maximum current, which is the Zener breakdown current, to prevent any damage. If you want to find the approximation in terms of the ideal Zener diode for troubleshooting or some preliminary analysis, then the breakdown region can be approximated as vertical. So when we draw the curve between the current voltage characteristic, the curve should be vertical and there should not be any knee voltage. Voltage is constant even with the varying current. If we ignore the Zener resistance, then this Zener diode is basically represented with the help of a battery shown by Vz. So the circuit simplification, if we talk about the Zener diode in the breakdown region, it acts like a constant voltage source denoted by Vz. These simplifies analysis, you can mentally replace the Zener diode with a battery of source voltage Vz. So if you have a circuit in the form of the Zener diode, so that can be replaced with the help of a battery whose voltage is given by Vz. Let us understand that with a problem. Problem number 1. The breakdown voltage of the Zener diode, which is shown in the figure, is 10 volt. So here you have the Zener diode, and the Zener diode is differentiated from a normal diode with the help of this Z symbol. So here you need to maintain a voltage of 10 volt. If you see the source, it is a variable source, 20 to 40 volt, and there is a Zener resistance of 820 ohms. You have to determine the minimum and the maximum current that will flow in the circuit. So the voltage is variable, 20 to 40 volt. Hence, the Zener diode can be replaced with a battery of 10 volt because that is the voltage being mentioned. So here we have replaced the Zener diode with a battery of 10 volt. And our circuit now no longer is having any Zener diode. So the current minimum value we can find out by taking the minimum value of the source. So minimum value of the source is 20 volt minus this Zener voltage, which is 10 volt, divided by the resistance 820 ohms. That gives 12.2 milliampere. Whereas the maximum current, if you want to find, then the maximum voltage of the source we have to take. The Zener voltage is constant 10 and the Zener resistance is also constant. So we get 36.6 milliampere. This indicates that output voltage stability, which is held constant at 10 volt. So here you have the output voltage, which is 10 volt constant. Source voltage is fluctuating from 20 volt to 40 volt, which is the input source. And the Zener diode behavior is increased source voltage leads to more Zener current. So if we see, when we change the voltage from 20 to 40 volt, the current 12.2 milliampere is changed to 36.6 milliampere. So there is an increase in the current when there is an increase in the source voltage. But the output voltage remains rock solid at 10 volt. So there is no change in the output voltage. So the conclusion is Zener diode ensure that there is a stable output voltage despite the change in the input voltage. So input voltage, even there is a change, the output voltage is constant. Now we put a load on the Zener regulator and see the operation. The Zener diode will hold this load voltage as constant in the breakdown region. Load voltage will stay fixed as at the Zener voltage because both will be in parallel. So VL and VZ will be same despite there is a change in the source voltage or the load resistance. So even the load is fluctuating or the source voltage is fluctuating, the load voltage, which is equal to the Zener voltage because both are in parallel, will be rock solid. That we will take with the help of the example of a circuit where the source you can see is fluctuating. The Zener voltage is given by Vz and it is connected reverse biased with respect to the source. The resistance is Rs and there is a load which is connected at the output whose voltage is VL. We can find what is this load voltage using the voltage division rule and the Thevenin's voltage. So Thevenin's voltage we can see using the concept of voltage divider rule, which we have discussed in electrical circuit theory and networks. So the source voltage multiplied with the load resistance divided by the sum of the total resistance, which is Rs plus RL, will give you the Thevenin's voltage. Now, the breakdown will occur only if the Thevenin voltage is greater than the Zener voltage of the diode. So the practical circuit, if you want to see, because this is the basic circuit, practical circuit will have a ground for the written path of the current. There will be a power supply. Now this is the rectifier maybe whose output is Vs, and there is a Zener voltage Vz and Zener resistance Rs and the load resistance Ri. So the current which is flowing in the loaded Zener regulator is given by the difference of the voltage from the source to the Zener voltage divided by the resistance of Rs. Is remains the same whether not the load resistor is connected. So even you do not connect any load resistor, the current will be there, which is Is. However, the load voltage VL, which is equal to the Zener voltage, because both are connected in parallel in the network. Hence, the load current, if you want to find, which is equal to load voltage divided by the load resistance. And the total source current now from KCL, Kirchhoff's current law, will be summation of the Zener current plus the load current. Hence, the Zener current you can estimate by taking the load current out from the source current. So Iz no longer is equal to Is. Earlier case you have seen that Iz and Is was equal, but as in unloaded regulator, but it is reduced by the load current value. So summary of the Zener regulator analysis that we have done under loaded condition is Is, which is the source current or the Zener current. We can say if it is unloaded, then it is equal to Vs minus Vz by Rs. The load voltage is equal to the Zener voltage because it is connected in parallel. The load current is given by load voltage by the load resistance, and the Zener current is equal to Is minus IL. Now see here, if the regulator is unloaded, it means the load current will be 0 and hence Iz will be equal to Is in unloaded condition. So this is the very basic introduction of Zener diode. In the next lecture, we will discuss more on Zener voltage regulator. Then we will move to other diodes like Schottky, varactor diodes, and many other additional diodes like pin diodes. You have tunnel diodes and so on and so forth. Thank you for now. See you in the next lecture.